Good morning, everyone. Welcome back to the OpenShift TV Coffee Break. Today we have a special episode about artificial intelligence with Optaplanner. Before going into the introduction of our special guest, let me say buongiorno, Andrea. How are you? Did you have your
Buongiorno from
coffee?
London. How are you? And today I'm cutting with coffee, so no coffee for me.
Oh, okay. It's a tough start, but it's a start, yeah. And Andrea, today our special guest is Geoffrey De Smet. Is the author of a popular open source software called Optaplanner. Geoffrey, welcome. How are you?
Thank you, Natalie. Good morning. I'm good. Everything's good.
Fine, good. Today if you look at the title of the show, it's Optaplanner AI Planning Optimization on Kubernetes. We will see how, and before we go into all the context, of course, we have our plan today, Andrea. We have some introductions, a quick round of introduction. Then we have some slides, and then of course Geoffrey brings us to the live demos. We have a preference here for live demos. That's cool. So Geoffrey, can you please introduce the topic for us? And for the people attending in the chat, please send your question. We will bring to the speaker. Please send your question in the chat, and we will bring to the show.
Yeah. So I'll talk about planning optimization, and that's quite. So it's a form of artificial intelligence, but it's not like deep learning neural nets or machine learning. It's actually an alternative form. And when I dive into the slides in a few minutes, I'll actually go show you the differences between those. I'll do some demos around that. I'll talk about vehicle routing problems, which is an advanced form of the traveling salesman problem for people who knew that from school. I'll talk about school timetabling, maintenance scheduling, employee rostering, all kinds of business problems and how you can solve them and optimize them with AI to basically reduce costs and improve service, as well as reduce carbon emissions and so forth. And any weighted function between those goals that you wanted to have. Right?
That's cool. Thanks for this quick intro, because I also had this question. What is the relationship between the artificial intelligence and Optaplanner? So it's good that we understand. And also, Geoffrey, we would like to understand today, what's the benefit of Kubernetes and OpenShift user using this software on their platform, how they can use the software. So we will see during the show. Thanks for this quick intro.
Sounds good. Do you want me to start with some on that first topic, the AI thing?
Sure.
Okay, I'll just if you can see my my screen.
Here we go.
Yes, we can.
Yeah. Okay. So I would just like to say that machine. Can I get rid of? Oh, just sorry about that.
For Firefox, I don't remember how to hide that.
Yeah,
maybe
no worries.
Auto hiding after a while.
Yeah, it will hide, I guess. Machine learning is a subset of artificial intelligence, and most people these days, a lot of people seem to forget that these days. So I'd just like to illustrate that for a minute, right? So there's a lot of AI algorithms out there, and you want to use the right one for the job. So presume you want to do a full text search. In Google or something like that, you type in the word cat, and you want to go through maybe on an internal system through all of your files, and you want to find the perfect file for that. Let's say, in this case, this PDF file that talks about cat, right? That's one problem. That's a form of an AI problem. Another one we all know is image recognition. You get a picture and you have to figure out what is shown on that picture, and the result of that, the answer of that is this is a dog, right? And another one, that's one I will be focusing, is the vehicle routing problem, where we need to go through a country, a region, and we need to send a number of vehicles to a number of locations, and we need to figure out in which order, and we go to which location at which time. And I'll talk a little bit more about the difficulties in that problem later. But what we want to get out of there is we want to reduce the driving time of these vehicles. We want to really make sure that they can do their job faster and they can do their job more efficiently, right? Now, all of these problems, these days, a lot of people say, okay, AI, that's machine learning. Machine learning is, in some cases, just neural nets, and so neural nets will solve everything. That's not true. In fact, if you want to do a full text search, what you want to do is you want to use a vector space model. If you want to do image recognition, you definitely want to use take a look at neural nets. And when you want to do solve the vehicle routing problem, take a look at the constraint solver at mathematical optimization. So every problem has its own, use the right tool for the right job, right? So if you want to do a vector space model, is of course more useful than just full text search. It's also useful for recommendation similarities. Neural nets are useful for any form of pattern recognition. Think about voice recognition, machine translation, and also for things like prediction and so forth, classification. And then constraint solvers are useful for not just vehicle routing problems, but some of the other problems I'll talk about, employee rostering, job scheduling, and so forth. And if you use the wrong algorithm for the job, so for example, a lot of people have tried to use neural nets on the vehicle routing problems, you will see that their results are poor. A typical neural net on a vehicle routing problem will not get above a 1% reduction in driving time, while the average constraint solver will easily get to 15% and often far more even. We have cases going up to 25% less driving time. So using the right tool for the right job is quite important.
It's almost as if neural nets were good at solving problems that a typical mammal brain can solve, but not a computer, and the other way around for typical constraint solver. It takes us a really long time, and we'll never get to the optimal solution if we did it manually.
Yes, absolutely, Andrea. So we've seen this, right? So a neural net, when is an image recognition algorithm a good one? If it can do the job of a human, right? If you say, okay, this is an image, and the human can recognize if it's a dog or a cat or something else, and the algorithm can get the same output, then it's a good algorithm, right? For vehicle routing problems and these kinds of decision-making problems, optimization problems, the algorithms do much better than humans. Why? Because humans, if you solve a vehicle routing problem, and I've actually tried this once in a class, we gave the entire group of people a traveling salesman problem, and they could not get it within 9% of the optimal solution, even though there were 30 engineers there who, smart people trying to actually solve this. It was just 60 locations. So the thing is that humans on average are actually quite bad at these sets of problems I'll talk about later, planning problems. And but if everybody in the room is colorblind, it's very hard to understand there's other colors than the ones you can see, right? And so if everybody if you're sitting around with a number of humans looking at the schedule of a vehicle routing problem, and everybody says, okay, this is the optimal solution or near optimal solution, you will actually group think that is the near optimal solution until you throw a real constraint solver at it, right? And you actually get a better results, and then everybody will be able to see, okay, this is a better results, but how do you get from that worst result to that better result? It's hard as a human. It's hard to see that. And of course, the technologies you can use for these depends, but I'm going to talk specifically about Optaplanner, which is an open source constraint solver, Apache license, sponsored by Red Hat. And I'll also show you, of course, how this works on OpenShift, and I'll show some use cases of this, right? So what is a planning problem? That's the kind of problems we're going to solve. It's when you want to optimize goals like maximize profit, minimize ecological footprint, maximize happiness of employees or customers, improve service quality and things like that. And you might want to try to optimize all of these goals or a subset of these or a weighted function between those. You might say, okay, profit is more important for me, but I still want to do minimize my ecological footprint. Why do I do that, right? Or vice versa. And when you want to optimize these goals, you have to do that with limited resources. You have a number of employees with certain amounts, with certain skills. You have assets like in the vehicle routing problem, vehicles, which with maybe different types, different sizes, and so forth. You have, of course, time, which is the most limited resource of all, I would argue. And in some cases, you also have budget constraints, like we can only make these kinds of decisions that are within budget. And there's constraints. These limited resources have constraints against each other typically, right? A driver needs to have a particular skill to go to a particular location, or needs to have a particular skill to drive a particular vehicle sometimes. There's working hours. For example, in a vehicle routing problem, when you're sending drivers to go to different locations across the country, they need to complete that trip within 8 hours or 10 hours, depending on the length of their shift. Or it might be longer in some cases, but we have constraints. And of course, a person cannot be in two places at the same time, and there's other cases like that. So and of course, what you can use for this is Optaplanner. It's an open source Apache license solver for that, and it will help you find better solutions in time and scale out. Now, one more slide before I get to some demos, some use cases, and then some demos. I think it's just a little bit about this. We have on one side, Optaplanner works for Java and Kotlin, and but we also have a Python implementation. I'll talk about in a second. And then if you use it in Java or Kotlin, you can use it in plain Java. You can use it in Quarkus, or you can use it in Spring. I'm going to focus today on Quarkus. Why? Quarkus gives us a number of benefits speed-wise, but also developer experience-wise, and I'll show those. And it also makes it easier to deploy it on OpenShift because it does a lot of the boilerplate stuff for you out of the box. Today I'm going to use Maven, but you could build this with Maven or Gradle, or you could probably build it with any other tool too, but these are the two major ones in the Java and Kotlin ecosystem these days. On the other side, we have OptaPy, which is a Python implementation of Optaplanner. It actually uses Optaplanner under the hood, but you don't see that as a Python user. You can write all of your code in Python and just run it. And it uses PyPy. It's actually deployed on PyPy, so you can just do pip install OptaPy, and you can start working from Python. Today, I'm going to show, when I'll dive into the code for some demos, I'll do that with Java. But any of the things I'm showing here today, you can actually do it in Kotlin or Python too. This runs on any of the platforms, of course, and of course we're going to run it on OpenShift. That's what we'll focus on today, right? So let's talk about an actual use case. So I've mentioned it a few times, the vehicle routing use case, just to clearly specify what it is and why you would want to actually solve this problem with a constraint solver. So we need to assign a number of vehicles, you can see them here, to a number of locations across the country. And we need to decide which vehicle goes to which location, and in which order do those vehicles go to those locations. And just think about that. If you have 100 locations, if you have 10 vehicles, how many possible ways could you do that? And to give you an idea, it's not a billion ways. It's probably more a billion ways. It's the number of the search space, the number of ways you can go to a number of locations with the number of vehicles is insanely big. It's a permutation on, it's a mathematical formula. I won't dive into that today, but it's fun if you go into the math side of things. And of course, what are the constraints with this? So there's a number of constraints. For example, the vehicle has a certain capacity. It can only carry 20 tons, and you have to deliver 10 tons here and 3 tons there. Or maybe it's not actually delivering items. Maybe it's actually, for example, installing cable in people's houses, technicians who are driving around the country. And in those cases, it's the amount of time they can drive around that is limited. They have to finish their job within 8 hours, and they might spend 2 hours here, 5 hours there, right? And then, of course, there's the driving time you have to take into account too. Or there might be requirements. For example, for this location, that's an expensive delivery. You need an armored vehicle. But that might also be a skill requirement you need, right? For this location, we need somebody who can install a cable, can install cable and internet. So we should send a technician with that particular skill set. You might have time windows. When a technician comes to install internet at your home, they probably promise to come in, between 8 and 12 o'clock, or in this case, between 8 and 10 a.m. And then, of course, the biggest one is you want to reduce the driving time, right? And so you might have this on all kinds of users, supermarkets, retail stores, and so forth. And so let me show you a demo of that. So what I've done here is I've started, and if there's any questions, feel free to interrupt me. Right?
No, Geoffrey, there's a comment in the chat from Donato.
Yeah.
Say,
Yes.
kind of agreeing what you say. No, neural network is the best case, can mimic the human brain, but usually they fails in the most tricky cases where human brain has no problem. And he say constraint solvers always achieve better result than human brain. Was a kind of exclamation, right? So yeah, it was a kind of Donato. Thanks for your comment, Donato. We know he's big fan of artificial intelligence and Optaplanner. This was the comment that we had so far in the chat. If any, we will bring it to you. So if you have any question, the topic looks really interesting. To be honest, I also sent a tweet live. If you want to jump into discussion, it looks very, very cool. Thanks.
Okay. Thank you, Natalia. So what I've done here is I've actually, let me just show you. So what I've done is I've gone to optaplanner.org. I've gone to the clone the quick starts code over here. And in here, there is the script, run quick starts from source. I've run the SH one, I'm on Linux here, but there's one for Windows 2, of course. And then you can run all of the and then it actually runs this application, which I've just shown you, which shows me all of the Optaplanner quick starts. Now, all of these can also be deployed on OpenShift, and I'll show that in a minute how to do that. But right now I'm running this one locally. And I've started up the vehicle routing demo here. So I've clicked the launch button, and now it's running on this port 8082. So I'll just go there. This is the vehicle routing example. And so in this case, we need to send from these two locations. We have a number of vehicles there. You can see the vehicles here on the side. We have to have different colors. And we need to send them to these locations here and we need to figure out which vehicle goes to which location in which order. So we click the solve button on the top right. And when we do that, Optaplanner finds a route. And you can see that the routes are still changing. It's finding better and better solutions as we give it more and more time. But here on the top, you can actually see the total distance, right? So you can see the more time we give it, the less distance it takes to actually do this. Right now, this implementation is optimized on distance, but in a real world use case, you would use Google Maps integration. We have a more advanced example that shows that too, how to do that, or OpenStreetMap integration. And then you would not use distance, but you would use time, right? Because you want to reduce the amount of travel time, typically. Now, if you reduce the travel time, you will reduce distance typically too. Usually it's a win-win situation, but there are some exceptions, of course. Now we've solved this for about 30 seconds, and we've reduced the distance down to 84 kilometers, right? So we started above 100 kilometers, I think even 105 if I recall correctly. So it really reduced it by maybe 20% on 30 seconds. Now, we actually had this in production all over the world for all kinds of vehicle routing cases, but one sticks out. There's one use case where the management was doing this for tens of thousands of vehicles in a continent, and they expected their driving time to reduce by 1%, and it was 25%. So imagine that your company can all of a sudden reduce their driving time by 25%. This was year over year, right? They were doing it for decades. They were doing it in a certain way with human planners or traditional algorithms, a combination of those. And then year over the year, they switched to constraint solvers. They tried multiple. They ended up with Optaplanner because it gave the best results. And Optaplanner year over year reduced their driving time by 25%. That was tens of millions of CO2 emissions per year less, which was nice. But they really liked the fact that it also reduced their, increased their operating efficiency by more than $100 million per year, simply because they were driving less around, so that people, the technicians, could actually do more work than actually help customers instead of driving around more. And that makes a huge difference, of course, as you can imagine. But it's not just vehicle routing you can solve. You can solve employee rostering too. So what's employee rostering? you need to assign a number of shifts, like a morning shift, an afternoon shift, an evening shift, to a number of employees. You can see here they have different skills. And you need to decide which shifts is done by which employee. So for example, this morning shift here from 6 to 2 p.m. is assigned to this nurse. Now, you have a number of constraints. Constraints like you require this particular, certain shifts require particular skills. So you need to have an employee assigned to that which actually has that skill. You have constraints that you can only have one shift per day for employees. Maybe in some cases you have employees who can actually do double shifts, but that might depend on the property of the employee, of course. You can have weekend work, no weekend work for certain things. And these are what we call hard constraints. That means we need to fulfill them. But Optaplanner can also deal with soft constraints. So soft constraints are things like, there's a day off request. This particular employee says, I don't want to work on Friday. She wants to take care of her grandchildren or something like that, right? Or his grandchildren, right? But so they do a day off request and they ask, I'm not going to take PTO, but please avoid giving me shifts on Friday. And if we can fulfill those, the employees are happier. And so we're going to try. So what we do is, what the algorithm does is tries to fulfill those as much as possible. Other things are things like forward rotation to make sure that the employees have enough sleep between two shifts, and that they don't have, they have to get weekends days. They don't have more than 5 consecutive shifts and things like that, right? And so use for hospital. This works for any kind of employees that don't work 9 to 5. So if you have a morning and a late shift, that's a typical case, but you could also have night shifts with or without weekend work. But any kind of situation where you see there are shifts, we need people to staff a particular job at a particular time, and it's not just 9 to 5. You will find that employee rostering is something that's very applicable. And so we try, so we have some benchmarks around this, traditional algorithms versus Optaplanner and so forth, a number of academic data sets. And what we see that on average, we reduce the number of rejected day off requests. In total, we fulfill all of the hard constraints, and there's a whole bunch of soft constraints, but most of the soft constraints, most of the impact is done by that day off requests. And we reduce the number of rejections by more than 50%. So basically, they can say, yes, you get your day off request 50% more, right? So instead of having to reject it 10 times, you only have to reject it 5 times a week. And that matters, of course, because it increases the employee retention, employee happiness, right? And of course, I have a demo for that. So let's take a look. Let's see if I started it here. The employee rostering, no, I haven't started yet, so I'll just start it. So it's loading right now. And let me check if I've deployed it on OpenShift. No, I've did another one on OpenShift, so I'll have to run this one here.
For the people attending, they can do the same quick start on OpenShift, right?
Yes, and I'll show you in a minute. So the next one is I'll show one on OpenShift. It takes a minute to build there, so I'm just going to show this one here locally. So in this case, we have a number of shifts, right? And you see the shifts here are all unassigned in particular departments. We have a number of employees we can see here, Amy King, Amy Smith, and so forth, with different skill sets, right? With when they want to work and when they don't want to work. And when we click let me go by location again. When we click the solve button, what you will see is that we start assigning these Chad, Elsa, you can see, I'll just stop it for a second, but it assigned this particular person to that shift. So it goes to this shift, Amy to this shift. And if you look at it per employee, you can see when they get their shifts. And you can see there's still a mistake here. We still have somebody in undesired shift, which is a soft constraint, which means we can break it. If you have too little people with the particular skills for that shift, but if you solve it longer, typically that will go away. And you can see here the score also. Okay. So, like I said, you can deploy any of these. So that's a really good question. So if you go to the quick starts, you will find. And so if you start from opt.org and you click on that link I showed it an earlier ago, so you clone quick starts code, right? You can find a list of all of those quick starts here. So if you go to the employee scheduling one, you see a screenshot. And And we actually jump into the README of that on this is the Quarkus employee scheduling one. Oh, I'm on that's the wrong button. This one, do I jump on that link? You will find here how to run it locally, how to package the application, but also how to host it in the cloud. So, so if you want to host it on OpenShift, what you do is you just follow these instructions. So you get a free developer sandbox on OpenShift. And then when you are into the web console, let's do this right now, we're going to add this. So I'm going to go to the web console of OpenShift. You can see I'm in the developer mode. You can see I have a couple of things running here, but the employee scheduling one is not in there. So what I'm going to do is I'm going to click the add button. I'm going to say, okay, import from a Git repository. Why does that work? Because if you look into the source code here of employee scheduling, you will see there's an S2I directory. And so this entire thing is built with Quarkus. So if you look into the POM, you'll see that we import Quarkus and it takes the sources and it builds that application. It's not that many files. It's just there's some tests of, but it's basically there's a few domain classes. There's a few test data, a test data class. There's a bit of persistence, a bit of rest. It's all relatively. There's not that many files here, maybe 10, 20 files. And then, of course, there's an S2I directory, which has all the information we need to deploy it on OpenShift, right? Now, this is a very simple deployment. It's just a simple app. I'll go through the architecture later. We have far more advanced cases where we're integrating with an ActiveMQ thread, a queue, or a Kafka and so forth, and where you can really scale horizontally as you get more and more data sets, more and more things you need to solve. But anyway, to get back to hosting it in the cloud. So what I'm going to do is I'm going to add imports from a Git repository here. You can do this right now if you want to. You can just follow me along.
Yeah, for people that want to follow along, I put the link in the chat to the developer sandbox for OpenShift. This is a free account where you can access your OpenShift cluster in a multi-tenant way. So you register for free, and then you can have access to the cluster like Geoffrey is showing in this moment. He is deploying in developer sandbox. And then you can follow along with the quick start, I guess. No, just step by step and doing as he's doing. I guess, Geoffrey, you're doing a kind of a source to image build. So you're starting from the repository, and then OpenShift will create a container image. I don't know if there are also Docker files in the source code that people can also use for creating the container. Also, OpenShift can use the Docker file.
Yeah. Right now we just use source to image for these examples, but we have a couple of other examples who go further. I'll end those two in a second.
Okay.
I'm not sure if I will be able to. I have it set up to demo them today, but let me show this one first. So what we do here is I will click add import from Git repo. I've already done. So I will use that simple approach right now. And so what I'll do is set Git repo URL. So in here we have to set the Git repo URL. So I'm going to just paste it in there. I'll show advanced options. Now the thing is, this is not in this employee scheduling here is not in the root of the project. The reason for that is because this is the quick starts repo, and there's more than just employee roles scheduling in there. There's vehicle routing in there and so forth. So you actually have to say it actually within. You have to actually set the context there. You have to actually say, okay, please go down into this directory of use cases employee scheduling. And so I'll do that, of course. I'll say here, you can see I have a bunch here already that I deployed earlier. But now I'm going to say, okay, please use cases employee scheduling. And because I've already deployed some of the other ones, I'm going to make sure that the name here is also unique. So I'm just going to call it employee scheduling. So that's it. So again, 3 things. Import Git repo, you give the repo URL, you say, okay, I want the context there to be use cases employee scheduling. If you want to do any of the other examples, you might say use cases vehicle routing and so forth. And then of course, give it a unique name and you do create. And as you can see right now, it's being started, the employee scheduling. So the one I just ran locally is now being actually run on OpenShift. As you can see, it's still building. So the build is running. So once that's done, we should be able to open it and take a look at it. While we do so, I just want to show you, I've shown you the vehicle routing one locally earlier, but I've actually built this before like an hour ago, I've deployed this. So now this is actually available and I can actually go here. It's the same thing as I ran locally. So again, I can click the solve button, it solves. But as you can see here on the top, this is actually live. So in fact, if we share this with the audience, you can actually try this right now on your computer. The only downside is that this demo is built in a way that there is only one data set. So if multiple users will be looking at this right now, they will be seeing this state. They will not start from scratch, right? And so, you can try it out. You can actually mess with my live presentation right now, probably, but it's all good. So let's get back to employee rostering. So I've just while we're here, let's see how this is going. I'll get back to that in a few seconds. It's building, it's creating the pod. The OpenShift developer sandbox is really nice to try stuff out, but you have to be a bit patient, of course, because the speed of the build and so forth is less than if you would have a dedicated paid for solution, of course. So that's why I'm going to just continue a bit, and then we'll see in a few moments when it is built there and available. I want to talk about another use case, maintenance scheduling. And here I'm going to focus more on how does it work? How would you use Optaplanner to solve these kind of problems, and what can you expect, right? So in the maintenance scheduling problem, just to introduce the use case, what we need to do is we need to assign a number of jobs, maintenance jobs, like work. This is for road maintenance specifically, so like work on the uptown streets, uptown bridge, forest road, airport tunnel. So these 4 jobs. We need to assign them to a particular crew to handle that, and to a particular date to start that work, and it will take a number of days to complete that work. So for example, the green job takes 3 working days, but the purple job here takes 4 working days. Each of these jobs can have an earliest starting date, that's their ready time, and has a latest possible end date, which is their due time. So every job needs to be done before a particular date, and it depends from job to job, right? So you can see here the green job needs to start at the 1st of November or the 2nd of November, because it cannot start before that. Its ready date is 1st of November, and it should be finished by the 5th of November. And because it takes 3 working days, that basically means the 2 options are 1st or 2nd of November. So what we're doing in this kind of cases is we give this problem to Optaplanner. There's also a bunch of constraints, like you can only do 1 job per crew per day. Once you start a job, you need to finish it. And there's might be soft constraints, like these two jobs, the uptown jobs, are in the same area, so we don't want to have them those in the same time, because that really increases the number of traffic jams into a particular area that is doing road maintenance. If you have multiple road maintenance jobs in the same area at the same time, traffic really goes crazy. So we do that. We give these problems to Optaplanner, and it gives us a solution like this. It tells, okay, you can start the green job then with crew A on the 1st of November. And after they finish there, they will do the airport tunnel. It laps over weekend days, of course. You can add in holidays to take into account too. And it will actually do the planning for you, taking into account crew skills and things like that. Now, how does the architecture look like? How does this, if you put it on OpenShift, what is the sample applications architecture? Like I've said, there's multiple ways to do the architecture. This is a very simple way of doing the architecture, and I'll just go through this one first. So what we've done is we've used Quarkus as a platform, and in there we've exposed a REST service under the hood that uses REST easy, but you really don't care. You just say, I want to expose that as a REST service. And we've used the browser application to go through that REST service and actually show the results of show how the schedule looks like from the database, because there's a database at the back, and we contact thread again an implementation detail with Hibernate. And so basically every time the UI refreshes, it goes through the REST service that goes to the database, gets the objects and sends them back over the REST servers to the browser. And then we add an Optaplanner here to actually do the optimization. So let me show that application for a second. I have it running here on OpenShift. So here we go. This is the maintenance scheduling solver. So that's that application. You can see it's running here on OpenShift. I have a number of unassigned jobs. In this case, I have 20 unassigned jobs. And you can see I have a number of crews to solve this. And if I look per job, I can see, for example, the downtown bridge needs to happen between the 6th and the 19th. So you can actually see what is the earliest starting date and what's the due date, right? The ready date and the due date of each job. You can see they're all unassigned. When I now click the solve button, Optaplanner on OpenShift will start assigning these for us. And you can see the quality of the solution here at the top. When this number gets better and better, basically this negative number gets closer to 0 or even above 0, you have better and better solutions, which means that there are less and less soft constraints broken. It's already a feasible solution because no hard constraints are broken. 0 hard means you can actually execute this plan, but reducing the soft constraints basically means the broken soft constraints basically means you get a higher quality solution, which you want, right? So you can see I get our results here. Let me just scroll down. All of the jobs are assigned. None of the jobs are assigned outside of their time that they need to be assigned. So no job is to assign too late or too early. And you can also see that the crews nicely have a work schedule. In this case, I am not front loading. So I'm not pulling the jobs to the front of the schedule, which I could be doing. I'm actually just leaving them where they are. In some cases, in some maintenance scheduling, you want to do front loading. You want to do all the jobs as quickly as possible. But sometimes you don't want to do that. You want to do just-in-time maintenance. For example, cleaning your house is a typical just-in-time maintenance. You don't want to if you've cleaned your house today, and you want to clean it once a week, you don't want to clean it tomorrow, even though you consider that next week. What you want to do is you want to clean it every 7 days, right? You want it just in time, just because before it gets too dirty, right? It's the same thing when you do maintenance on elevators or when you do maintenance on electricity grids or railroads and so forth. You typically want to delay even on airplanes, you want to delay until the moment you would start endangering or anything, right? Until the moment the risk actually starts kicking in. So for example, for airplanes, there's a requirement that they need to have maintenance every 48 hours. So when you do a maintenance, you don't want to do a maintenance an hour later. You want to do it 40 hours, 45 hours later. So you hit your 48 hours requirement for safety regulations. And you want to have a little buffer there, but for efficiency reasons, if you would do it every 24 hours, that would be a very high expense. Of course, in non-regulated environments, you need to, there's a lot of business constraints to take into account, and you should not, increase the risk too much, of course. But that's a business decision. So to get back to this is how it works. This is the thing, and if I want to show you in the code, if we go to the use cases and we go to maintenance scheduling here, as you can see, you will see that this is the same setup as the one I showed for employee rostering, also with S2I. But I promised you there's also use cases where we go much further than this simple setup, which I've shown here. So than the simple setup of sending something to the relational database. So this is use cases. They all work like this. They just want to show the use case. But in the technology directory, so we have a directory use case in the quick starts, but we also have a technology directory. One of the technologies directories we have, so we have here all of those use cases I showed us with Quarkus. But we have other cases like if you want to use Kotlin instead of Java with Quarkus, or you want to use Spring Boot, we have those available. If you want to use Python, this is actually a link to our Python quick starts, where we have one for vehicle routing, employee rostering, and so forth too on Python. We even have Python notebooks for there if you want to try with that. But the one I want to talk about is the ActiveMQ one. So this one is a far more advanced example. This one actually has Docker images. And what it basically does is we have don't have an image here, but we do have a blog post around it. So let me just find the blog post. This is yeah. So what it does is it says the number of clients can have a planning problem, but instead of having it for instead of solving one maintenance scheduling for one or solving one employee rostering for one hospital or vehicle routing for one region, you might actually have multiple regions. You might have multiple hospitals. You might have multiple regions where you do maintenance scheduling. And all of these, you want to be able to solve those, and you want to be able to make sure you scale horizontally a number of solver servers, right? So you want to have, for every problem you have, you want to start up a pod, solve that, and send the response back to the things. And so one approach there is you use the ActiveMQ broker. You send in your solver requests, your problems into that ActiveMQ queue, and then your pods pick those up, solve those, and send them back. So that's one thing we're working on. But these days, we're also working on another thing. I wish I could show you today, but it's still under development. But we have, oh no, that's not the one. I don't have it public yet, but we're actually working on also an approach where you have an operator, an Optaplanner operator for OpenShift, and then it will actually scale to 0. So when you have no pods running if no data sets are in the queue, but as soon as data sets come into the queue, Optaplanner will start up. The Optaplanner operator, Kubernetes, basically Knative, will start up a pod and solve one of those data sets for you, which is a very different architecture from what I'm showing here. But you can take this use case, you can take the maintenance scheduling use case, you can see in the code how we solve it domain-wise and so forth. And you can easily cut off this top part, this REST service, and replace that with an approach that works like this. Cut off the relational database part and just say, okay, here's my data set. That's how we solve it in Java or Kotlin or Python. And then hook that into what we will have with the operator, for example, right? Any questions so far? Anything in the chat?
We put the link in the chat of the blog post. We don't have at the moment the question. If you, folks, if you have any question, please send in the chat. We will bring to the show. Andrea, I think you're mute. Okay.
I had. Am I on mute now?
Yes.
No, it works.
Can you hear me now? Okay, so I have a number of questions, actually. And one is, there are a number of different use cases that you show here. Mm-hmm. And I would imagine that they cover let's say, different classes of problems that can be solved. And so they would be the starting point for somebody who wants to solve it. They'll have to try and see which one of these problems is similar, and instead of starting from a model from scratch, they can have an example of how the model was created. Are all these examples in Java then, or do you have the examples also implemented in, let's say, Python, or for the benefit of those that may find themselves, new generations that find themselves more familiar with Python, especially the AI crowd?
Yes, very, very good question. So we have something called Optapy, and so that's optapy.org. And in fact, if you are on the Optaplanner website, there's a link to this too, if you just click on this Python thing here, right? And we have Jupyter notebooks. So you can try, we have Jupyter notebooks. This is one that's starting up right now, where you can try Optapy with Python. But just to jump into the quick starts here, let me just jump to the quick starts. I think we should have a link here. Right, so this is not the quick starts, but I'll just go there. Quick starts. So this is the Optapy quick starts. These are in Python. And so, for example, I was talking about the employee rostering, employee scheduling one. You can find the exact same example here written in Python. So you can see this is the domain classes. Instead of Java, it's Python. We have an entire if you go back here to the documentation I showed earlier, we have an entire quick start on how to build this school timetabling example, which is the one I was going to get to now, and how to build this in Python. You just you pip install Optapy, and then you start coding. You follow these. So yeah, we support that too these days. It's a bit slower though.
That's what I was going to ask. If you then have to create a system that works in production at scale, you may want to then, if you've done all your experiments, time to implement it in Quarkus, maybe.
Yeah. So Quarkus. So you can we have different levels of speed, and we're always making Optaplanner and Optapy faster and faster, of course, right? The devil is in the details. So Optapy right now is significantly slower than Optaplanner. That's why we're actually giving it a different name. That's why we're not calling it Optaplanner, but Optapy. But we're working on improving that. We actually have a nice PR that reduces the performance gap. It's still there, but it will reduce the performance gaps significantly. The reason was that we had internally, so there was some ping pong between the codes, and we're reducing that with some bytecoding techniques. Now, if you go into Java Kotlin world, you can just use Optaplanner in plain Java or plain Kotlin. But if you then say I'm also using Quarkus, it actually goes a step further, because what Quarkus does, so Optaplanner needs to use reflection in Java to get to your data in your domain classes. But Quarkus actually avoids the reflection. Instead of using reflection at runtime to go into those classes, what it does is when you build your project and and then at that point in time your domain classes are known, it actually generates bytecode to avoid reflection and go into those classes directly, and gives that bytecode to Optaplanner, which takes advantage of that. And that gives an additional performance benefit when you use Quarkus over just plain Java or Spring Java, right, or plain Quarkus and so forth. Kotlin and so forth, right?
We do have another question. Question from the Pinga Gallery. Donato is asking, how does the solving workload scale in an OpenShift cluster?
Oh yeah, a very good question. So that's why I had that too many tabs in there right now. So I'll just use a new one. So that's why we had that. How does it scale? So if you follow the approach that was shown here, right, with that ActiveMQ approach, this scales well horizontally in function of your number of data sets. So for example, if you have a vehicle routing problem, but you have a large company, you have multiple countries, multiple regions, 8 provinces, and you have one vehicle routing problem per, let's say, region, area, or state. What you do is you say every problem you have, and sometimes you have cases here where they have hundreds or even more of these kinds of data sets. They send them into the solver, into this ActiveMQ request. And then you will horizontally scale your number of solvers together with the number of things that are coming in here, right? If you will be using the new operator, the Optaplanner operator, then we will start a pod per data set and so forth. So that will scale horizontally with that. But the problem is sometimes you cannot, you don't want to do partitioning, because if you take a planning problem and you cut it in pieces, and I can illustrate that. That's actually quite interesting to show. So I can actually illustrate that. So let me just do it for a second. Yes, this one. Okay. So if you take a planning problem, yeah, I've shown the solution already, but just bear with me for a second. If you take, this is a traveling salesman problem. We need to send one vehicle to all of these locations, to all of these dots. And we need to find the shortest line that connects all of these dots, basically. If you say we split that up into 4 pieces, and we solve those 4 pieces optimally, and we put those 4 pieces back together, you get this solution, right? So this is a single line that goes through all of these locations. But it's not the optimal line. The optimal line is actually shorter and looks quite different, as you can see. So this is the big problem of all of these optimization problems. You cannot say I have a big problem, I cut it up in pieces, I solve the pieces in the independently, divide and conquer, map, reduce, whatever you call it. And then in the end, I put them all back together and I get an optimal solution. And that also means that if you have one data set you need to solve, and not, let's say, hundreds, right, you can't really scale that to a number of pods. What you can do, however, what Optaplanner does support, is within one pod, scale the solving of it across multiple cores, right? And so we have something called multi-threaded solving, which other constraint solvers don't have, or don't have, at least for the kind of algorithms we use. And we can scale that. We can scale with the number of cores. We have some limits there, but we're working on those and we're still improving those. But that means that is still limited by the number of physical CPUs on a machine that pod is scheduled to. So we're still investigating how we can, if you have one data set, how we can scale that further. But if you have multiple data sets, that's not an issue at all. So yeah, it's a good question. It's a good question.
Earlier, you actually mentioned that you're also working on a Knative version.
Yes. So the Optaplanner operator that's scaling to 0, right? That basically means if you have no data sets in your, so if you're working so this is an ActiveMQ broker, right? But if you have that doesn't use ActiveMQ, this is the ActiveMQ example, which you can find here, but the Optaplanner operator approach does not use ActiveMQ. It's actually based on Kafka, but when you have a number of data problems come in, it's going, if there's no problems in submitted, it will not be using any pods. As soon as pods come in, it will actually scale up. The typical scale to 0 approach, right? If that makes sense. If you want to follow that development around that, and we are working in here. That's the Optaplanner operator. So we're working on, it's still experimental, as you can see, and there's more information around that here. Somebody in my team, Radovan in my team, is working on this. Progress is good. I have not played with the latest version yet myself, so I'm not studying. I'm not demoing it to the day yet. Give us some time when this comes out of experimental things. It's very, very early on, but in a few weeks, few months, probably a few months, we'll have them. We'll have a much better thing, and I'll happily demo that for you too. Any other questions?
I have a question, Geoffrey. So this is really cool, and you showed us many use cases. Actually, I have two questions. I've seen that Optaplanner has been used also maybe as a demo for scheduling, vaccination slots. So do you have any reference, like if it was used for real vaccination appointments?
So many of our use cases, so we have a lot of production use cases for all, for like vehicle routing, employee rostering. It's used all across the world. But for vaccination scheduling, that actually we don't have that in production that I'm aware of. It's a very cool use case because we actually were scheduling we were running with data sets up to 200,000-300,000 people being decided in a single schedule. So the number of the size of the problem was just much bigger than we usually deal with, because deciding how to assign tens of thousands or maybe 100,000 locations to tens of thousands of vehicles, that's a big problem. But once you go to, we even went to 500,000, if I recall correctly, so 500,000 decision variables, where each decision variable was able to, this is the vaccination scheduling case. That was a really interesting case. However, vaccination scheduling, it was very time windowed. We had a good implementation, but we started with it way too late. So we still have this demo ready, and so when the next pandemic hits, we will be ready instead of like this time. But we were too late for this one, to be honest. We started way too late with creating that example.
Okay. Okay, I hope we don't need another pandemic to try it. We can try, for flu vaccination or those kind of stuff.
Yeah.
But that's really cool. I was impressed also when you did your article. No, that it could be implemented in this way. And I have another question, Geoffrey, because we close up. How do you see? Is there a reference architecture for using Optaplanner and any MLOps pipeline? Do you have any architecture blueprint where you can automate all this stuff?
We don't have a blueprint yet. We should probably think about one. Architecture-wise, if you look at the Optaplanner quick starts, so let me do that. That's there. I'm in the wrong. Okay. Go to Optaplanner quick starts. This is basically where you want to look at how it's a good way to set things up. The use cases I've shown earlier are very simple setups where you're solving, where you go to a database and bring it back. But in the technology one, the one I showed about ActiveMQ is quite interesting. As soon as we have one with the operator, it will probably appear here too with the Optaplanner operator. So these are basically these are our reference architectures to look at. You have a couple of different options. But what we see, the big enterprises that use Optaplanner, they typically go for a setup like this one, where they set up that queue because so they don't connect their UI directly to the Optaplanner solving bit, but it's actually just they have a microservice of Optaplanner that pulls from their data store, solves the problem every night, and sends it back, right? And that, of course, scales to the number of data sets they have. And so this is a good approach there, basically. Quite interesting to note. A minute ago, you asked, what kind of production usage you say. It's always quite interesting to hear where Optaplanner is being used in production. And so, for example, in certain countries, if you get a court hearing scheduled, Optaplanner will decide which judge you get. For example, in Belgium, if you go to a pharmacy in the weekend, Optaplanner will decide which pharmacy is on duty in your region to be open in the weekend.
Oh, wow.
So yeah, this is actually affecting people's life for the better. Like for example, in the vehicle routing case we have in a big continent, it is really saving tens of millions of CO2 emissions, and also deciding which technician is sent to your house to do certain jobs, right? So the impact is worldwide, and I regularly meet people that tell me, okay, we've used Optaplanner for this or that use case. The really cool one I heard very recently is that, and there's a public article about this, is that to decide which fighter pilot for airplanes in the US gets decided with a couple of algorithms, and one of them is Optaplanner. Which training goes to which. So it's used all across the planet. Planning problems are everywhere when you start seeing them, and you can really improve those schedules to get better schedules for the employees, for the stakeholders, the company, the organizations, the governments, and so forth, right? And really deliver better schedules.
And there are many other interesting things in Optaplanner that obviously we didn't have time to look at today. For example, the whole concept of continuous planning, and how would you build a service around it, especially on OpenShift? But maybe that could be topic for another talk.
Yes, definitely. That's a talk in itself. Continuous planning, real-time planning, non-disruptive planning. We have a whole concept.
Absolutely.
You can based on your needs, you can pick the ones you need, and they all fit together, right? Just pick the ones you need, and absolutely, Andrea.
Geoffrey, you should definitely come back to the OpenShift TV coffee break, because we want to hear more about Optaplanner. It's cool. It's very great that we hear that open source is affecting for the good people's life. Optaplanner is used in many use cases, like the pharmacy, as you mentioned, logistics. So open source, which is helping people's life and also businesses. This is really good to hear. Thank you, Geoffrey. This we kind of ended our time, right, Andrea? We
yes,
are out of time.
I just wanted to remind you guys, everybody that wants to join us next week. Next week we're going to have Ian Lawson that will give us a guide to Tekun for beginners. So if anybody wants to get their feet wet with testing for the first time, that's a good starting point.
Awesome. So we will come back to the OpenShift Coffee Break next Wednesday at 10 a.m. here. Today in the schedule, there's the Ask an Admin at 5 p.m. European time. If you'd like to follow along through OpenShift TV. Other than that, folks, see you on next Wednesday. Thank you, Geoffrey, for staying with us today. It was a really great session. If you want to connect with Geoffrey, you have his Twitter account. And if you want to hear more about Optaplanner, of course, there's the Optaplanner website. Remember, you can try all the quick start that Geoffrey did in the sandbox. So you can go into the website, go to the quick start, create your sandbox account, and try Optaplanner and start implementing your use case. Thank you, everyone, and see you soon.
See you next time.
Thank you.